Good morning, students. As you know very well, we have started Unit 8, Aldehyde, Ketone and Carboxylic acid. So today we will continue the unit and we will discuss about isomerism of aldehyde and ketone. First of all, you should know that what is isomer? What do you mean by the isomerism? Isomers are the compounds which have same molecular mass, but different arrangement of the atoms. Different arrangement of atoms or elements are known as the isomers, and this property is known as the isomerism. Students, there are mainly two types of the isomers: structural isomer and stereoisomer. We can further classify stereoisomer, we can further divide into optical isomers, okay, in enantiomers, in cis and trans. So today we will discuss about the isomer of the aldehyde and ketone. First one is the chain isomer. Chain isomers. What do you mean by the chain isomerism, in which one compound will be in straight chain, other may be in branch chain? So aldehyde show the chain isomers. Like student, if you have CH3, CH2, 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 CHO. What is this? 1, 2, 3, 4, 5. 5 carbons are there, means it is pentanal. It is pentanal. So I can take one carbon in one or more carbon in chain also. In branching I can take like this: 1, 2, 3, 4, 5. So here you can see, here 5 carbons, 1, 2, 3, 4, 5. 5 carbons are there, and hydrogen 3 to 5, 7 to 9 and 1, 10. 10 hydrogens are there and 1 oxygen. Here we will also calculate here carbon 1, 2, 3, 4 and 5. Again hydrogen 3 and 1, 4, 3, 7 to 9 and 1, 10. 1 oxygen. Means both have same molecular formula. If their formula is same, means they have same molecular mass also. But student, here one compound is present in straight chain. And other compound is branched. Here one carbon is placed in branching. So here what is name of this? Its name is 1, 2, 3. 3-methyl-butanol. So due to change in the chain, their property is also changed. So students, aldehyde show the chain isomer. In chain isomer, some compounds will be in straight chain and some will be in branch chain. We can make more isomers also. Okay, we can make more arrangement also if possible. If we talk about the ketone, do they show chain isomer or not? For ketone, students, there is a condition. In case of the chain isomer, there should be minimum 4 carbons. There should be minimum 4 carbons in ketone. If carbon are less than 4, then they do not show the chain isomer. For example, if I have CH3CO, this is acetone. Acetone is common name. This is acetone. What is the IUPAC name for this? For this IUPAC is 1, 2, 3, propanone. We need not to write the position because ketone, its list position is 2. Okay, either it may be at 3 position, 4 position, but its list position is 2. We can write propane 2 on, it is not wrong. But directly we can write propanone also. So students, here, can you arrange this in branching? You cannot. Okay, so if there are 3 carbons, then it do not show the chain isomerism. But if carbon are 4, then they show, because I can write no, there are more bonds. In this way also, but these are metamer. This is not the chain isomer. This is not the chain isomer. So in which way we can write for showing it into the chain? It is possible or not? If we write in this way, CH3, C double bond O, 1, 2. This is the same thing. If we write in this way, this is also the same thing. C double bond O, CH3. This is also same thing. Means there should be more than 4 carbon atoms, but not more than, because we cannot write in chain. If we want to write, then what will happen here? They will either show metamer or it is forming. If we write in this way, then it is forming 5 bonds. But it is the tetracovalent. So we cannot form bond more than 4. Okay. So students, here carbon should be more than 4. Then they show the chain isomer, otherwise they cannot. Clear to you or not? Then ketones can show the metamerism. What do you mean by the metamers? What do you mean by the metamerism? Metamerism means different number of alkyl groups attached to the same functional group. For example, if we have CH3, C double bond O, CH2, CH3. Or we have like this, CH3, CH2, C double bond O, CH2, CH3. So here you can see, here carbons 3, 4, 5. 5 carbons are here. 3 to 5, 7 and 10 hydrogen and 1 oxygen. Here also 1, 2, 3, 4, 5. 5 carbons, then 3 to 5 to 7 and 3, 10 hydrogen and 1 oxygen. So here molecular formula is same. Means molecular mass is also same. But what is the functional group? Here functional group is ketonic group. Okay. So here this one. This one is the ketonic group. You can see here only one alkyl group is present. Methyl is present in this side. And here number of carbon atoms are 3. Okay. Here in both sides there are 2 carbon chain. Clear to you or not? So this type of isomers are known as the metamers. These are known as the metamers. Mean there are different number of the alkyl groups present inside of the functional group. These are known as the metamers. It is clear to you or not? Then student, next isomer is the position isomer. Position isomer. Position isomer not shown by the aldehyde. Aldehyde do not show position isomer because aldehyde group must be present at the one position only. Okay. It may not be present at 2, 3 or 5. Means in between it cannot present. So it will present at one position. Okay. Because one hydrogen must be present there. So they do not show the position isomer. But ketone show. For example, if I write butane, or we can write pentane. Pentane 2 on and pentane 3 on. 3 on I can write. So 1, 2, 3, 4, 5. 5 carbons are there. Here pentane 2 on means at position 2 there will be ketonic group. So this CH3, CH2, CH2, CO, CH3. This is pentane 2 on. And if we have ketonic group at position 1, 2, 3, there are 6 carbon atoms. So, this one is the pentane 3 on. Both have same molecular formula. Both are the isomer. But what is the difference in between them? Here difference is that here ketonic group present it as carbon 2. Means position of ketonic group is 2. So it is known as pentane 2 on. And here ketone is present at position 3. So it is known as the pentane 3 on. Because here change in position take place. Change in position. Next one is the functional isomers. Functional isomers are those which have same molecular formula. But functional group will be different. Functional group will be different. For example, if we take CH3, CO, CH3 and we have CH3, CH2, CHO. Here you can see carbon 1, 2, 3. 3 carbon, hydrogen 3 and 3, 6 and 1 oxygen. Here 1, 2, 3. 3 carbon, hydrogen 3 and 2, 5 and 1, 6. 1 oxygen. In both cases, molecular formula is same. So molecular mass is also same. But students, here functional group is ketonic group. But here, which one is the functional group? It is aldehyde group. It is aldehyde. So it is aldehyde. So propanone and propanol, they show the functional isomers. In case of the position isomer, functional group should be same. In case of the position isomer, functional group should be same. Only position of functional group change there. But in case of functional isomer, here functional group also change. It is clear to you or not? Yes. Next isomer is, students, tautomers. Tautomerism. Tautomerism. In case of tautomerism, it is most important isomerism. Both aldehyde and ketone. Both aldehyde and ketone show tautomerism. But what is the condition here? What is the condition here? There must be present alpha hydrogen. Because here either methyl shifting or hydride shifting take place. Clear or not? So students, if we have like this, CH3CHO, CH3CHO. So here alpha hydrogens, there are 3 alpha hydrogens because this is alpha carbon. So there are 3 alpha hydrogens. What may happen here? Here, you know very well, this oxygen is more electronegative and pi bond is also present here. Okay, so it will attract the electron towards itself. If it will attract the electron towards itself, then positive charge will attain on this carbon and negative charge will attain on this one. But student, here deficiency of electron will take place here. Then what will happen? This bond will shift here and this will shift here. What will happen then? Then CHH. This bond is going to shift it here. So this one is double bond. Then this bond is going to shift at oxygen. So there will be negative charge on oxygen. And this, because it is losing its electron, so it convert into the H positive. Then due to electrostatic force of attraction, these positive and negative, they will form bond between them. So what will happen? Here CH double bond. See, this H attached to this oxygen, OH, H. Now student, try to understand. This is known, keto group is here. So this is known as the keto form. But here at the same carbon, double bond, and at the same carbon, alcoholic group is also attached. So because double bond is present here, so for double bond, which suffix we use? We use in. So in plus. At same carbon, alcoholic group is present. For alcoholic group, we use the all. So in plus all. 2 vowel, we will not write together. So we will cut this one. So this is enol form. This is the enol form. Clear or not? Here, which one is the more stable? Keto. Keto form is the more stable because in enol form, both double bond and alcoholic group are present at the same carbon, which make it unstable as compared to this one. Clear or not? So this is known as keto-enol tautomerism. Clear? What will take place here? Here hydride shifting or methyl shifting take place. It is clear to you or not? Okay. Ketone also show. If we talk about ketone, for example, if I have CH3, COCH3, this also show tautomer. Why? Because alpha hydrogen are also present here. Okay, so here again this bond can shift here and this can shift here. So finally we can get in this way CH2 double bond COH CH3. This is keto and this is enol. Students, we write the keto-enol tautomer in equilibrium, because here both keto form and enol form, both are in equilibrium. So we will show in this way. Both are in equilibrium. So we will show in this way. Clear to you or not? So in tautomerism, there must be alpha hydrogen. Presence of alpha hydrogen must be there. Then they will show. It is clear to you or not? So aldehyde show chain isomers. Aldehyde ketone show position isomers. Aldehyde do not show the position isomers. Ketone show the metamerism. Aldehyde not. Clear? Aldehyde do not show metamerism. Tautomerism shown by both aldehyde as well as ketone. There must be present alpha hydrogen. Okay, students. So today we have done isomerism of the aldehyde and ketone. I hope these are clear to you. Okay. So this is enough for today. Thank you. Have a nice day. Structure भी करवाना